Assalamu alaikum class. I hope that all of you are well and safe in your homes inshallah. Today in lecture 25 of our course Signals and Systems, we are going to discuss system function algebra and block diagram representations using the Laplace transform. In lecture 15, you have already discussed how to make block diagrams of a linear constant coefficient differential equation or simply a differential equation, and in this portion of our text we'll see how we can use Laplace transform to simplify that representation and get further representations of the same system function. So we have discussed in lecture 23 that system functions can be used to simplify three types of LTI system interconnections, which were the series connection, the parallel connection, and the feedback connection. The series connection is also known as the cascade connection, and as we know that in the series connection we have two systems or two or more systems which are connected in such a way that the input to the next system is the output of the previous system. So we discussed that for such a case, although the time domain representation was h1 convolved by h2 of t, but if we draw such a system through a Laplace transformation, it becomes one system where the transfer function h of s can be broken down into a product of two transfer functions h1 of s and h2 of s. Similarly, when we discuss the parallel connection, where the parallel connection is a connection where all the systems connected in parallel get the same input, and the output for a parallel system or for a system which is represented as a parallel sum of several systems, the output is the sum of the the output of all the individual systems. So such a system can be, in the transform domain, such a system can be presented as one combined system with all the transfer functions being added. Now in today's lecture, we'll see that using the transfer function, how can we make a block diagram representation, or how can we realize our system. This discussion is going to cover rational transfer functions only, and we'll see that we'll make different representations, but actually there's no unique way of realizing a system, and each form has its own merits and demerits, which you will discuss in your DSP course when you will be using or making systems for a discrete time function, that what is the advantage of this or disadvantage of each representation. In signal systems, we'll only be discussing three of these representations. All of these different block diagram representations, the direct form, the cascade form, and the parallel form, will be derived from the same transfer function. And in the following slides, we'll see that how can we derive three different forms or multiple different forms from the same transfer function. So the steps we follow for block diagram representation can be outlined by, say, we have a transfer function which has the same order of the numerator and denominator. So this is our nth order transfer function with the same order for both x and y terms. So let's say we take a third order system. So a third order system can be represented as this form. Now we'll stop at this point and we'll discuss that whether can we draw a block diagram from this first expression or not. Yes, we can. In this case, this represents a simple differentiation operation, and we can use a differentiator to make a block diagram. But we remembered that we discussed in lecture 15 that an integrator is better to realize or better to implement than a differentiator, So for these reasons, we'll be using integrators to make a block diagram. Or we can say that the Laplace transform for an integrator is 1 by s. So we'll be converting this form in s to a form in 1 by s so that we can realize it through an integration operation. So I take s cube common from both the numerator and denominator, and this is what I get at. So this means this is a b cube b3 plus b2 by s, which means this term comes with a single integration, this term comes with a dual integration, or after a dual integrator, this term comes after a triple integrator, and so is true for the denominator. So if we want to make a direct form is directly derived from the transfer function. In the first or the most basic form, which is known as the direct form 1 realization, we implement the numerator first and the denominator second. Or you can say that we divide our transfer function into transfer functions h1 of s and h2 of s. We just saw on the starting slides that for a cascade representation, we say that the overall transfer function is a product of two transfer functions. So this is kind of a cascade where we have two transfer functions which are being multiplied. But when I'll be trying this form in the example to follow, you'll see that this form is similar to the basic block diagram you learned making in lecture 15. We can also realize, since convolution is commutative or multiplication is commutative, so we can implement this part before this part. So we can say that h of s is h2 of s into h1 of s. So this means that we'll implement this part or the poles before the zeros. Both this form where we implement the denominator or the zeros first and the numerator or the zeros term afterwards is known as a direct form 2 form. So both direct form 2 and direct form 1 form result in the same transfer function, but they generally behave differently from a viewpoint of sensitivity to parameter variations. Now we come to the next form, which is the cascade and parallel realizations. In the previous direct form 1 and direct form 2 realization, we saw that we implemented the transfer function as it is, the numerator and denominator terms as it is. But the transfer function can be expressed as a product of or a sum of smaller terms or first order terms or second order terms. So a situation where the transfer function is divided into many small first order terms or a product of or a sum of smaller first order transfer functions is known as a cascade or a parallel realization. So where the transfer function will be divided as a product of terms, we'll call it a cascade transfer function, and where it will be divided into a sum of first order transfer functions through partial fraction expansion, we'll call it a parallel realization. So let's do all these realizations by using a for the transfer function given in this example, we have to implement it through direct form 1, direct form 2, cascade form and parallel form. So let's try to solve this example. The transfer function is given by h of s is 4 of s plus 28 divided by s squared plus 6s plus 5. So for the first step, we have to take out s common so that this transfer function can be expressed in terms of 1 by s rather than s. So we say that h of s is equal to, I take s square common for both numerator and denominator because the highest order of the equation is 2, or the order of the system is 2. This becomes 4 by s plus 28 by s square, and this becomes 1 plus 6 by s plus 5 by s square. So this gets cancelled, and this is the transfer function that we have to implement for direct form 1 and direct form 2. So in the direct form 1, we say that we implement the numerator or h1s before this. So for df1, our h of s is 4 by s plus 28 by s square, which is h1 of s, into 1 by 1 plus 6 by s plus 5 by s square, which is h2 of s. So let's draw this. We remember that the block diagram is like a big box which with x of n entering on one side and x of t entering on one side, it's a continuous time system, and y of t as the output. So in the black box for the transfer function, my xt is coming as the input. And then what happens is, I don't have a direct term or a term with no s. The first term comes with an integrator. So this is 1 by s, and this term is being multiplied by 4. Then the next term again comes with 1 by s, and it is being multiplied by 28. Both of these terms get added. The output of the black box was y of t, and this part was the feedback part, and I'll advise you to just quickly revise lecture 15, because from lecture 15 we can recall that this part comes with the coefficients come with a minus sign. You can say that it's a minus sign or an opposite sign to what is appearing in the differential equation or the denominator. So this is minus 5. This gets added. This is the direction of arrows, and this part gets added to it, and this is your direct form 1. So in this direct form 1, this part is your h1 of s, and this is h1 of s, and this is the h2 of s. Also we can see that all of this, we can say that it's a one system. I am drawing it with a pencil. So the input of the system was x of t, and the output is y of t. If you want, or as I could have done, was deriving separate equations for each of these and proving that these equations indeed lead to the block diagram, but I haven't done this because I think that we have already made these block diagrams in lecture 15, and we know that this system could have been further represented as one system, and we could divide the whole process into saying this branch as W of t, etc. But now you are mature enough in signal systems that you understand that this is one system and this is two system and this is the other system, and this overall is the direct form 1 representation. Now let's make a direct form 2 representation, and for direct form 2 representation I'll start with this equation and I'll just reverse the order. So for direct form 2, what do is we will reverse the order. So I'll be writing this transfer function again. For df2 h of s. Now we'll implement the whole term or the denominator term first, plus 5 by s square into 4 by s plus 28 by s square. I'm going to bring the figure again, previous figure again. Now what I'll do is I'll pick up this block and bring it here, and pick up this block and take it there. So I'm just picking up this block. This is the first step. I'm just picking the block. Xt is the input, yt is the output, and now just that block is being copied here in the first step. Since I want to draw a neater diagram, I want to draw two diagrams on this page, so I am making the diagram in an inverse manner. You can make, it's not necessary that you draw arrows backwards. You could have made the system first and that system afterwards. So the other part is this. One by s is 28. This part is 4. This gets added to this and exchange. So this is the, so far this is how the diagram looks. This block is 1 by s and this block is also 1 by s. I'm going to bring the figure again. You can see that I have just taken this block here and this block here. Now we observe that 1 by s is here and here. So what we can do is we can replace this operation by a single integrator and this operation by a single integrator. So our form becomes, I'm going to combine the integrators now. This is one integrator, this is the other integrator, this goes like this. This has a multiplier of -6. This has a multiplier -5. Over here there was nothing, so I don't have to make this branch. And over here we have 28, and this gets added. So this is y of t, and this is our resultant block diagram. And this block diagram is known as a direct form 2 with the integrator line common in between. So what is the difference between direct form 1 and direct form 2? The first difference is that in the direct form 2, the output terms, over here in fact here should be an arrow, the output terms are the coefficients of the output or the pole coefficients are drawn first, and the coefficients of the numerator or the coefficients for the input are drawn afterwards. Now we can see that in this form the number of integrators is minimum because the equation was a second order equation and we just used two integrators. So this representation is also known as a canonic form. I'll not be asking you to what's a canonic form, but this is just an extra term that you should know that TF2 is also known as the canonic form because it has the minimum number of integrators. So after drawing these two forms, let's come to the third form, which is the cascade form. These two forms were comparatively difficult to make. Cascade form is a very easy to implement, draw. So in the cascade form, we discussed that we divide our transfer function, the given transfer function, into a product of first order transfer functions. So the given transfer function 4s plus 28 by s square plus 6x plus 5 can be divided into 4s plus 28 by s plus 1 into s plus 5. I have divided the second order transfer function into a product of first order terms. Now any of these can be termed as h1 of s and any of these can be determined as h2 of s. I say that and h1 of s is 4s plus 28 by s plus 1 and h2 of s is 1 by s plus 5. So our overall system is a cascade of two systems, which is 4s plus 28 by s plus 1 into 1 by s plus 5, and this is our output and this is our input. For example, you don't know what I expect, so you say, okay, no, I want to draw this 1 by s plus 5 first, and this part 4s plus 28 by s plus 1 afterwards. So that's also fine. This is also the correct cascade connection. For example, you say that no, I want to take this 4s plus 28 with this s plus 5. So you say I make something like this, 4s plus 28 by s plus 5 and into 1 by s plus 1 yt. So this is also fine. Or say no, we want to implement now this 1 by s plus 1 first and 4s plus 28 plus divide by s plus 5 afterwards. So this is also okay. So from one transfer function, I made these 4 cascade combinations of 2 systems. We could have also divided this into a cascade of 3 systems, H1s, H2s, H3 of s. So any realization is possible. Students usually ask me that, madam, which of them is correct? So all of them are correct. And when it's, obviously I can't say that implement this system first when I ask you a question like this. So any system you make, as long as you understand the concept that for a cascade connection, there are 2 transfer functions such that the output of the first transfer function is the input of the second transfer function. If you realize this concept and make me any one diagram, that's fine. So finally we have the parallel form. Just a note for this. For example, the denominator was such that I was unable to divide this into a system of real coefficients. Say this has complex roots. So in case you have a third order system or a second order system which has complex roots, then you wouldn't be able to make a cascade form. And then you divide it into a, say, second order, say it's a third order system, and it has one real pole and two complex poles. So you just divide it into a first order system and a second order system. And this will be explained in, when I'll be looking at the slide again. Let's make the final form, which is the parallel form now. The transfer function h of s is 4s plus 28 by s plus 1 and s plus 5. Now for the parallel form, we divide this transfer function into a sum of several transfer functions, and we use our favorite formula, which is the partial fraction expansion. So I like to take the liberty of dividing this through partial fractions into you can try to see whether you get the same factors or not. Now this is first system and this is the second system. So we have our input x of t. The first system h1 of s is x by s plus 1, and the second system is, I'll make a slightly larger one, 2 by s plus 5. So this is the second system, and you can say that this is a summary and say this comes with positive, this comes with negative, and this is our output y of t. Now say you ask me, what if I put a negative over here? So I want to draw a parallel system like. This time I'm using this block in the upper branch and this block in the lower branch, and I'm using a simple summer, not two different operations here. So this is our transfer function, and this is the second type of parallel form you can draw from the same transfer function. So in summary, the crux is that a system can have several cascade forms or several parallel forms, and all of them lead to the same transfer function. And there's no hard and fast rule as if to say which is the correct parallel form. All of them are correct. So you make any form, that's fine. I hope that through these questions and solving these examples, you'll be able to solve the questions given in your lecture as part of your lecture 23. You'll be able to solve them easily. And the summary is these. If we have cascade and parallel implementation of higher orders, we could group it to factors. Not all of them are at the first order. For example, if we have a third order function, we can make it as a cascade of a first order and a second order factor. I can ask you that divide the system or implement the system as a cascade of two systems only, and it's a fourth order system. So you'll be making it in a cascade of two second order systems. Okay. These are some practice problems which you have to do. And this concludes our today's lecture. Thank you.